Let's now take a closer look at the fundamental theorem of calculus. It's commonly abbreviated the FTC, fundamental theorem of calculus. It's what we've been talking about. It's the fact that the integrals and derivatives are actually inverses of each other. Now, what we're going to do is go over this with a couple of examples, two different types of examples. It's actually called the Fundamental Theorem of Calculus Part 1 and Part 2. They sort of say the same thing, but you apply them in two different ways. So consider the following. Let's say we have a function, g of x, and we're going to have this equal to the integral, say, from 1 to x of some other function like t squared minus t cubed dt. Okay, so we've seen integrals, we have an idea of what they are, but now the question is, what is g prime of x? And what's interesting about this is we want the derivative of an integral. Okay, the integral is an antiderivative, right? I like to think of up and down. You usually think of powers, right? When you integrate, you go up a power. Like if it was just x cubed to x cubed. But when you take the derivative, you go down a power. So when you take the derivative, so here you're taking the integral, you're going up a level. When you take the derivative, you go back down to the level that you're already at. The fact that the derivative and integrals are inverses of each other implies that when you take the derivative of an integral, the prime, the derivative, and the integral part cancel each other out, and you're simply left with this function. Because it is a function of x, that's what it is. It's a function of x. It's the function, but it's with x. Now, the fundamental theorem of calculus, part 1, is very specific in that it needs to be a single x value, okay? It's not supposed to be a, we'll look at it when it's like x squared or x cubed, it's actually a little different, okay? But these should match, and this is typically like a different variable. Okay, it's a little weird, but you get used to it. Let's just look at a similar, kind of like the same thing, but a little differently. What if we say this, right? It's the same idea. What if we take the derivative with respect to x of the integral? Maybe this one's going from 0. Now, if this is an x, this also needs to be an x. Okay, so it's just a match. If that was a z, that should be a z. And then we've got something in here. Like let's say it's our sine squared theta d theta. Okay? Well, this is just like the one above it. The derivative and integral piece cancel each other out, and you're just left with the function. But it's in terms of x. So it's not sine squared theta, it's sine squared x. Okay? So, very beautiful, fundamental theorem of calculus. These end up in calculus as sort of like special problems. Okay? And the reason why I say special is because you're typically computing derivatives or computing integrals. But you will see some special setups, and what will happen in some cases, like end of year, you're doing a test, like the AP test, and you see this, you just start trying to integrate it, and it's very difficult usually, when instead you could just say, oh, wait a minute, I'm supposed to take the derivative of an integral. That means I don't have to really do anything. Now, what is the piece where you do have to actually do a little more? I mentioned, well, what if this isn't just an x? What if it's the following? What if it's something like, we want d dx of the integral, instead of just x, right? Let's say it's x squared now. And then this could be any number actually. It's kind of weird, it's like -1. And then again, we've got some kind of function, okay? Well, let's say this is e to the sine theta d theta. Okay, so how do we deal with this? Because the fundamental theorem is very precise, like the way it's defined. I'm not putting the definition up here, but it's basically defined that this is x. You know, if you say this is just some function f, then g prime of x is f of x. define with that being x. Well, now it's x squared. Okay, so how do we deal with that chain rule? So the chain rule, you can do the following. You can say, okay, I'm going to make a substitution. I'm going to say this is d du, let u equals x squared. So this would be now u negative 1. Now note that it doesn't affect the theta piece. So this will still be sine theta d theta. But by the chain rule, this is the same as du dx. Right? Because if you just look at the d du and the du dx, ignore us in the middle. The du's cancel out and it's d dx. That's how you use the chain rule. And so what we did here is we did a substitution. We clearly substituted u from x squared. So u equals x squared. And so u equals x squared implies that clearly du dx is 2x. And so basically that's what you do. If it's not just a regular x, if it's something else, then you basically have to multiply by the derivative of what's in there. And note that this also works for just regular x, it's just that dx dx is 1, okay? Or d dx is 1. But when you do it with x squared dx, well that's 2x. Okay, so the final answer here, now if you look at just this first part of it, that is just, now it's in terms of u, it's e to the sine u. Well, what's u? Remember, u is x squared. So we don't want to write u, you could, but we want everything in terms of x, because the problem is written in terms of x. And so it's x squared, and then times 2x. Okay, that's the correct answer. Now, for the second part of the fundamental theorem of calculus, I want to sort of just highlight an example that will help justify it a little bit. So consider like the following. Consider we have here a graph, and let's do one that we can easily get the area of. You know, how about something like, let's just even do y equals x. Okay, so this is y equals x, and let's just say it's going from 0 to 2. Now, we can get the area of this. So for instance, the question of, this is sort of interesting, the question of like, what's the integral of x dx from 0 to 2, we can do either, we have options. We can do an antiderivative, or we can just sort of like say, what's the area of the triangle? And triangle is 1/2 base times height. And if it's y equals x, if that's 2, this is 2. And so 1/2 of base times height here would be 1/2 of 2 times 2, which is 4, which is 2, right? Because half of 4 is 2. Okay, so that's simple enough. But now what if we look at it from just say, what if we go from 1 to 2? Okay, well, this is a little bit interesting. Okay, so we're going from 1 to 2. So we're changing the problem now. What's the integral from, say, 2 to 1 of x dx? Now here's, okay, first of all, it's a trapezoid. You can get the area of a trapezoid. But I want to emphasize it in a different way. You can take basically the big triangle, okay? Right, I'm just going to put circles in here to indicate big triangle, the pink, and you could subtract the area of the green triangle, right? Overlap, which is just this piece. And it's clear that if you subtract the one from the other, you actually will get the correct answer. So what that tells us, let's continue this one up here. So if we take as an example the integral from 2 to 1 of x dx, we do the following, okay? We take the antiderivative, which is x squared over 2. Now, in all of these cases, note, you don't need a plus c. In this one, it was a cancellation. You don't actually use a plus c in this one because what you do is you basically put in what you do is you evaluate this integral It's at 2 minus the integral at 1, okay? So that's how you do it. You evaluate it at x equals 2, you subtract out x equals 1. And the point is that if you add a plus c, and you evaluate it at 2, and then you evaluate at 1, those c's are actually going to cancel out. Okay, so you don't actually need the plus c. This is why people forget the plus c's. If we always put them in this case, we would remember. So this basically reveals, and this visualization is here to sort of help justify why the subtraction. Because when we first did examples, it was always going from 0 to something, and it turned out that the antiderivative was giving us the right answer, going from 0 as the area under the curve. So if you go from two other numbers, not including 0, the one subtracted from the other, both going to 0, actually work out to give you the correct answer. So you do the 2 squared over 2 minus 1 squared over 2, and we see that's 2 minus 1/2. So that's 4 halves minus 1/2, so it's 3 halves. Now, we could do a check, okay, because we said, well, look, it's the area of the trapezoid, right? And so if I want to look at the area of the trapezoid here, remember the trapezoid formula? It's like 1/2 b1 plus b2 times the height. And so here you'd have verticals. And so this would have a length of 1, the other has a length of 2, so that's in total 3. Right, but the height here would be this length, which would actually be 1. And so we do get the 3 halves, okay? Now, look, if you're doing integration and it's like an easy area, you can use that to kind of help you, but this would be the normal way. And this, in effect, is the second part of the fundamental theorem of calculus. You know, it just simply says what you do to integrate from one value to another, you take the antiderivative, you plug in the first value, and you subtract the other. That's the second fundamental theorem of calculus. It says you can get the entirety, which again is interpreted as area under a curve, but again, not strictly area because you have the negatives, by just plugging in the endpoints, okay? And that's what this is attempted to provide justification of. So let's just do one final example, okay? What's another one? Using the second fundamental theorem of calculus. Okay, let's go with, how about this, integral from 0. Actually, let's not do 0, because 0, well, we could depend on what it is, right? How about this? 0 pi over 4, and we're going to do the integral of the sine of theta. Okay, so antiderivative. It's negative cosine, right? Because cosine derivative is negative sine. It's negative cosine theta, evaluated at pi over 4 and 0. Okay, so you gotta be a little careful with the signs here, okay, when you subtract. Negative cosine of theta, cosine pi over 4 is root 2 over 2. That's negative root 2 over 2. But then minus the negative cosine theta is a plus, and cosine of 0 is 1. Okay, so that would be the answer, and if you wanted to simplify it, it's plus 2 over 2. You could reorder it as positive 2 is the 1, 2 over 2, 2 minus root 2, all over 2, totally equivalent. And that's the fundamental theorem of calculus. So going forward, what a lot of calculus is going to be is actually the fundamental theorem of calculus part 2, which is to compute these different integrals that you're going to be dealing with. And you get a lot of practice, and you'll learn some different techniques to compute them. I tried to say before, you can't really compute every integral given to you. It is a deep dive. There are lots of methods. Advanced classes discuss more advanced methods. There are even approximations, like Riemann sums. There are other approximations that are commonly used today that people use. You know, with computers, you can get great approximations. But that's the new topic. It's integrations, it's antiderivatives, it's areas under curves, and you can use those ideas to even come up with additional applications like getting all volumes. And so integration is fundamental. And in symbols, right, these all have the same symbols. That S means summation, okay? It is a summation. Like with the visual, it's a summation of a bunch of infinitely thin rectangles. In approximations, it's a summation of a bunch of very thin rectangles, okay? When we do volume, it's going to be summation of a bunch of areas. Anytime you're doing extensive summation, you're doing integration.